Since the recording was not on, I'll introduce myself again. So this is week 7 for NPTEL TA live interaction session for Rapid Manufacturing course. And this is Palkin Gupta, PMRF scholar and PhD scholar in Department of Material Science and Engineering, IIT Kanpur. The course instructors are Professor J. Ram Kumar and Professor Amandeep Singh, Department of Mechanical Engineering, IIT Kanpur. And the course ID for this course is noc22-me74. So in this live interaction session, we can always interact with each other. You can always stop me in the middle and ask any kind of questions relevant to the course. So we'll first briefly recap through what all was taught during this week. That is the first two lectures, which were based on extrusion and liquid based processes, and the third and the last lecture for this week, which was based on laminated objects processes. Okay, so and then we'll be solving some sample problems which will in turn help you to solve your weekly assignments, and I hope those sample problems are fruitful such that you are effectively able to solve your assignment problems. Okay, so let us begin with So let us begin with the extrusion and liquid based processes. So as the name suggests, this technique is based on extrusion of a material that is in the liquid form. So extrusion means any material that you can extrude through a fine nozzle or a fine pipe like that. Okay, so you do icing on the cake, simple example, or you take out toothpaste from the tube, that is extrusion. Okay, so these are the extrusion techniques. So in these extrusion techniques, we need to maintain constant pressure. Okay, so constant pressure is important so that you have uniform feed rate or uniform material deposition on your substrate, or mass flow rate is constant. And why is this needed? This is needed because if your mass flow rate is not constant, then what will happen? If anybody can answer, if mass flow rate is not constant, what is going to happen? Okay, so if mass flow rate is not constant, then you will be having non-uniform deposition of material at different places, like having a larger chunk of material at one place and a smaller chunk of material at the other place, which will cause a roughness and discontinuity in your structures. Okay, and this also helps us in maintaining a uniform diameter or uniform cross section of the material that is being extruded. So uniform diameter of the material being extruded. Okay, and the material that is being extruded, that should be in a semi-solid state. Why semi-solid state? This is because extruded material that should be in semi-solid state. Why a semi-solid state? Because if it is too liquid towards the liquid side, it will just flow away and will not retain its shape. For example, water. If you try to deposit water in a filament form, suppose like this, suppose this is your nozzle and you are extruding water through it, and if you try to deposit it like this, so what it will do, it will just lose its shape and flow away. So this is too liquid. Okay, and if it is too solid, then it will be really difficult for you to move your extruder head and deposit the material uniformly on the substrate. So that is why it needs to be in middle, so that it doesn't flow and lose its structural integrity, and as well that it isn't that much solid that it is difficult to move your extruder head. Okay, and then it should solidify in the ambient atmospheric conditions so that it retains its structure. So on the left, this is a very basic schematic of these extrusion based processes. So this green colored is a filament which is going inside, and these are the pinch feed rollers. Okay, these are pinch feed rollers. So what they do is they rotate like this. Okay, and when they come to this position, they just push the filament downwards through the towards the extruder or the nozzle. So as they rotate in this direction, this filament is pushed downwards because of the resulting forces. And as it moves downwards, it reaches this heating chamber where it is converted into a semi-solid or molten-like state. So this state is very like kind of a jelly form, okay, and not a complete liquid one. So at that stage, it is heated using resistive heaters, inductive heaters, capacitive heaters, etc. And then it is extruded through a nozzle. And it is finally extruded through a nozzle. And this nozzle diameter can vary. Okay, like you can have 0.1 mm nozzle die at one time or 0.5 mm nozzle die at other time. Okay. Now, another important aspect is, as we had seen in the last lecture, that in SLM processes, it is necessary to maintain overlapping of the layers. We saw that suppose if this was your layer, so it was, and these were your track scans. So it was necessary that whenever you print this second layer of yours, a portion of the first layer also melts. So this particular portion of the first layer also melts. And why it is so? So as to ensure good bonding with each other. Similarly, similar to this case, uh, the extrusion should be made in such a way that the newer incoming material solidifies or bonds with the already existing solidified material on the substrate, so that you have a solid structure. Okay, and now there are two primary approaches when we are using an extrusion process. First is that you use your temperature so as to control the state of the material. Like here in this heating chamber, you are using temperature so as to maintain the semi-solid or molten-like state of your material. Okay, and where material is then liquefied and then it flows out. And another approach is to use a chemical change to cause solidification. Okay, so where there is either reaction with air or photopolymeric reactions, etc. So basically, you have two approaches for extrusion based processes. Okay, two approaches. Now, what are those two approaches? First was, what was the first? Controlling the state of material using temperature, what we saw in this heating chamber. And next approach is to apply chemical change for solidification. For example, the photopolymers like we saw in the last lectures. Okay, so there is a chemical reaction that goes on, and it finally brings out to a solidified state. Okay, so there were photopolymers that when UV light or a visible light was projected on them, the photoinitiators initiated the reaction and polymerization, and then there was cross-linking of polymers to finally result in a solidified part. Okay, now let us move to the basic principles or the sequence of operating a extrusion based process, or the features of this process. So it is a kind of a 7-step process. First is the loading of the material. Second is the liquefaction of the material. Third is application of pressure to move the material through the nozzle. So, okay, so let us first see these 3 steps. Now, firstly, it is a loading of the material. So here we see towards the right in the diagram, which has been taken from the lectures itself. So we have this filament material. This is usually a polymer, or can be a ceramic or metal. Okay, any form wire. Okay, basically a wire. So it is a loading of the material. First is that you just insert this filament into this chamber. Okay, if you don't insert it, then how the rollers are going to move and then feed it into the system. Okay, so this is the loading of the material, that is insertion of the filament into the nozzle geometry. Okay, uh, is anyone having any doubts or any questions till now? Okay. Then a next step is liquefaction of the material. Okay, now when this material has been inserted, now there is this liquefier chamber. Liquefier chamber, that is, this material is in solid form, and here it is liquefier chamber. That means here there is a conversion from, okay, this is not visible, from solid to liquid state. So this conversion is taking place. So for this conversion to take place effectively, what is required? Heat is required. So here heating is happening. Okay, and when this heating occurs, this material, it goes into a, in this portion it is in a semi solid or molten state. Here the temperature is such that it always remains below the melting point of this material are maintained. Okay, temperatures less than melting point. Okay, so this was the liquefaction of the material. We have seen loading, we have seen liquefaction. Now third is application of pressure to move the material through the nozzle. Now we have loaded the material, we have liquefied it. Now we have to push it so that it comes out of the nozzle and makes way for further material to be liquefied. So for that pushing we require pressure. And how will that pressure be applied? Using this pinch feed roller system. So these help in application of applies pressure to move the material ahead. All right. Okay. So now your pressure is applied. How it applies? It kinds of rotates. So this will rotate in this direction and this in this direction in a synchronous mode. Okay, rollers rotate in opposite directions. So one is rotating clockwise, so other is rotating anti-clockwise. Rollers rotate in opposite directions to push the material or push the filament. Okay. Now, when you have already pushed this material, then it has to come out through this nozzle tip. So that is now your extrusion part. So it is in a molten state, and then there is this nozzle tip of yours. And from here, when you are applying pressure from behind, this material is being extruded. Material is being extruded, okay, in the molten state only. Okay, so here your material has been extruded. Now where to extrude this material is a very important question. Okay, you cannot just randomly extrude it anywhere and everywhere on your substrate or the platform. You need predefined paths and actual positions where you can just deposit this. So how are these paths defined? So these are predefined paths and they are defined as per your CAD model. If your CAD model says deposit in the form of a circle, so this plotting will be done in a circular manner. Okay, so the nozzle or the extruder head will traverse a circular path. If it says it is a square cross section, so this extruder will traverse a square path. Okay, so it all depends on the CAD model and the geometrical information that you supply to the software or the machine that are connected to each other. Okay, so plotting refers to the movement on the movement of the extruder on the platform. So it can move in X direction, Y direction, or Z direction. So here your Z axis is shown. So it is always this vertical. Now X and Y axis are on this platform or in the plane of this platform. Okay, so if this is your Z, so this is your X and this is your Y. This is the coordinate system, right-handed coordinate system that is followed. Now you have started to deposit the molten material. Now it should bond either with itself or the secondary build material to form a coherent solid structure. What does this mean? Like suppose you have already made outer boundary, okay, of this circle, suppose. Now you need to print inside it. So whatever you print inside it, suppose in this pattern you are printing, so all these points, these green one, should be connected to the points on the blue circle. Okay, green points should bond to blue ones. And why so? Why should they bond? So that there is there is good bonding of the material and you get a solid structure. If this doesn't bond, then what will happen? Your blue circle or the outer boundary will be one part and this inside infill patterns will be a second part. So you will not get a coherent solid structure. Instead, you will be getting two different parts. And the last one is inclusion of support structures to enable complex geometrical features. So suppose you want to print some overhang parts basically or internal geometries. In that case, you always require certain kind of support structures This has been repeated innumerable times that for the geometries, complex geometries, where there are certain overhangs or internal cooling channels or any such structures, complexities, we require support structures. Okay. So, are these steps involved in extrusion-based 3D printing clear to everyone? Any questions? Okay. So, we'll move ahead and we'll see the plotting and the path control part now. So, there were in this particular topic, that is these basic principles of extrusion based processes. Certain formulas have also been discussed during the lectures, which pertain to the extrusions, the material deposited during extrusion, the feed rate, the material flow rate or the velocity. Okay, so they were discussed during that, and certain equations for solidification as well, and shear stresses as well. Okay, now we'll move to plotting and path control. Okay, so all these processes use a generic STL file format, and this enables us to easily extract the slice profile, or it easily enables us to just slice the CAD geometry into multiple layers and extract the information of one particular layer. So which gives us a particular information about the coordinates and the points where material is required in a particular layer. Okay, now in most systems we have a control software which determines how to fill the material within the outline. Like suppose you want to make a cylinder, so you will first have the outer boundary of it, and then there are softwares that will decide how the internal part of that cylinder will be filled. Like, will it be completely solid, or will it be having only 50% of the spaces will be occupied with the material, or just the 10%, okay, which is known as the infill density. Okay, and this information is really crucial as it determines the strength and the physical properties and the mechanical properties as well. Okay, so we need to control the path and plotting. Okay, so and this also helps us to maintain the accuracy of the path. Okay, so like uh, the way we tend to develop these G codes and the paths of the material, the accuracy and the precision, they are also defined by this. Okay, so we have two ways of extrusion. First is to maximize the precision, which is the left image. This one is to maximize precision. Whereas another way is to maximize the strength of the material by controlling voids. This one is to maximize material strength by controlling voids. Okay, so these are the two ways. Okay, so and usually what happens is, firstly outline is made. So as a first step, outline is generated, and in the second step the inner parts are filled. Okay, and now this outline is generally made at a very low speed than the internal part. Okay, this is made at a very low speed. Okay, now uh, then your internal part is made by having certain intersections, and then these intersections are ordered in either way. One is to maximize the precision, or in a way so as material strength is enhanced. So if we see in the first part, we are maximizing the precision of the geometry by having no overlaps like here. This is kind of more or less a perfect kind of a geometry. Okay, and then so okay, so this is kind of precise. This one is precise, but here you see this void is really big. This is a kind of void where there is no material. So this will work in deteriorating the strength. Now another strategy will be to maximize the material strength by controlling the voids. Now this void needs to be controlled. So if you see, as we move to here, we see that this void is reduced in size. Now this void is reduced in size. What they have done is they have inhibited a bit of overlap, allowed some amount of overlap. Okay, so when they are allowing this kind of overlap, so at these places here, good bonding between different layers is ensured. Okay, and this good bonding ultimately results in better mechanical strength. Okay, and then we have second step where internal parts are filled. In continuation with this first step, we have the second step. Now we can notice that this precise control of extrusion, as where to extrude, where not to extrude, is a complex function of multiple number of parameters, and these parameters can be input pressure, in temperature, nozzle diameter, material characteristics, gravity and other factors, and temperature that is built up within the part. Okay, so we'll see how each variable affects this one by one. Okay, so input pressure, this is changed more of on a regular basis, and it is tightly coupled with other input control parameters. Okay, so when you change the input pressure, what changes? The speed of the filament going inside the liquefying chamber and coming out of the nozzle. So changing the input pressure will directly change the output flow rate. Okay, so and as that is changes, and as this output flow rate changes, a number of other parameters are also affected, because it directly changes or directly affects the flow of the material. So input pressure is directly associated with the output flow rate. So this directly affects the output flow rate of the material. Next we have is temperature. So maintaining a constant temperature within that liquefying chamber is very necessary, so that the viscosity of the material that is being melted or changing into molten state remains constant and uniform. Okay, so constant temperature will be the ideal situation. Okay, and it should not, like, slight variation can be there, like plus minus 1 degree or so, but there should not be large fluctuations. Small in actual systems, small fluctuations are always inevitable. Okay, but you see, large fluctuations should always be avoided. Sorry. Okay, so temperature, this should be maintained constant. Okay, and as the heat builds up, uh, there is a slight pressure drop to maintain the same flow rate. And why the pressure drops? Because since the material has now changed into a kind of molten form, it flows in an easier manner than before. And as it can flow at a faster, comparatively faster rate now, there is a drop in pressure, which causes the filament to immediately seek into the nozzle and fill up the space which is having lower pressure. Now, next parameter is this nozzle diameter. Okay, and this is constant for a particular build. Okay, so whenever you go on to build any material, any part, nozzle diameter remains constant for one single operation at least, until unless you change it for the other one. And they also allow interchangeable nozzles, that you can vary the nozzle diameters, and that would obviously affect your flow rate and the feature size that you can make, the resolution, all these will be affected. Now, fourth parameter are the material characteristics. Okay, so material characteristics information are important for controlling the process parameters, and these characteristics include viscosity, which is one of the very important parameters in extrusion based processes, because this would help in understanding the flow behavior. Okay, if you know the flow behavior, you can predict how the material will act. Then second last is the gravity and other factors. So when you do not apply any pressure, and since the material is in a molten state and the pressure has dropped within the liquefying chamber, your material can be extruded under the effect of gravity as well, because pressure is lower inside and it is higher outside, so it can just flow through the nozzle because of gravity. And surface tension of the melt and drag force at the internal surfaces of the nozzle may retard this effect as well. And the last one is temperature buildup within the part. All parts start to cool down as soon as they're extruded. Now, different geometries cool at different rates. Okay, so it depends on the complexity of the geometry. So large structures will hold heat for a longer time, and small one will lose out the heat at a faster rate because of the surface area to volume ratios. And so this affects in the final properties of the material. Now let us see some other liquid based systems that were discussed. One was bioextrusion, which was discussed in a bit detail, that was used for scaffolding and other purposes. And the other systems that were discussed were contour grafting, non-planar systems, FDM of ceramics, stereolithography, jetting systems, and high viscosity jetting. Now in FDM of ceramics, basically instead of a solid filament, we extrude ceramic pastes. Extrusion of ceramic pastes. Okay, which can quickly solidify under atmospheric conditions. Which can quickly solidify under atmospheric conditions. Okay, so that is basically a ceramic paste or a slurry, maybe an aqueous suspension of any kind of ceramic, or its suspension in any of the solvent like ethanol, acetone, etc. Okay, and then the resulting parts that are made, they can be fired using high temperature furnaces, or they can be parts can be sintered at high temperatures. Okay, and then these resulting parts, they have very good geometric properties and other properties as well. Okay, so this was FDM for ceramics. Now we have the stereolithography in the extrusion form, wherein material containing photopolymers, a photopolymeric resin, it is extruded through a nozzle and then it is solidified using lasers. Okay, so in this photopolymeric, so this is stereolithography based on extrusion. Extrusion based stereolithography. This is extrusion based SLA. Okay, now these photopolymeric resin comes out of nozzle to be solidified by laser. Then we have jetting systems. In jetting systems, material is extruded in the form of small droplets, multiple droplets, like in a jet. What you see, there are small droplets that are dropped onto the substrate. Material is jetted through a series of jets. Okay, this material is jetted through a series of jets and then it is cured using a UV lamp. Okay, and then we have high viscosity jetting, which is basically the jetting technique only, but the material is at a very high viscosity. Okay, now what are the limitations of this FDM process? Okay, so it is impossible to draw sharp external corners or internal corners as well. Sharp external and internal corners. Why this is so? They always exhibit rounding. So any feature that is smaller than the nozzle diameter, that cannot be made. Okay, and there is always a rounding. So suppose you want to make uh, uh, maybe say an extrusion of say 1 mm diameter. Okay, so this is your height. Okay, and your nozzle diameter is itself 2 mm. So whenever it extrudes the smallest amount of material, it will always be in 2 mm diaphragm. So you cannot make this feature, or it will always be rounded. So similarly at the corners as well. So this is very small radius, and since the nozzle has a finite diameter, so this will always take up the rounded form. The actual shape produced is dependent on the nozzle acceleration and deceleration characteristics and the viscoelastic behavior of the material as it solidifies. Okay, so how fast the nozzle is moving, how fast it is retarding, and how is the viscoelastic behavior of the material as it solidifies. Does it contracts or does it expands on solidification? All these factors determines the actual shape. And feed rate, that depends on the liquefaction rate and the extrusion pressure. There is no other way to control the feed rate. It always depends on how fast the material is being liquefied and how much is your extrusion pressure. An increased material flow rate causes increase in mass, which makes it difficult to move the extrusion head. Okay, so whenever there is uh, an increase in your flow rate, what will happen? You will start to deposit larger amounts of material at a single place, and what this will do is this will make it difficult for your extrusion head to move forward. Okay, so that will basically act as a resistance. So your larger amount of material at a single place creates resistance for the movement of extrusion head. Okay, so this was all about the extrusion based processes or liquid based process, liquid extrusion based processes. In case you have any questions, you can ask if anyone is having any questions. Okay, so we can move forward to the laminated object manufacturing. So what is this laminated object manufacturing? So in laminated object manufacturing, we talk about stacking 2D sheets of materials over one another. Okay, so here say you are having a paper, and stacking multiple papers over one another will give you a kind of cuboid. So that is what is termed as laminated object manufacturing. So similarly here these 2D sheets can either be polymers or they can be metallic foils. Okay, so these can be your materials when you are having 2D laminated sheets. So it is a layer by layer lamination of paper material sheets cut using a CO2 laser, where each sheet represents one cross-sectional layer of the CAD model of the part. So whenever, as I have been giving example from the beginning, suppose this is your cube, okay, and you discretize it into multiple layers. Now you have these sheets, these layers are your sheets now, okay, and now you cut these, and so there are big chunks of sheets. Now you cut these sheets into the desired dimensions. Okay, and once you have cut the sheet, you stack them over one another and bond them together using multiple techniques, one of the multiple techniques, and then you can have this entire cube or the cuboid. Okay, because of the construction principle, only the outer contours are cut. So for example, for one of the layer you need to cut a square cross section of say 1 centimeter by 1 centimeter. So only these outer layers, outer contours will be cut, and nothing will be done in this internal area. So there will be nothing done, only this outer contour will be cut using the laser. And now these sheets can be so there are two methods. First is they can either be cut and then stacked over one another, or they can first be stacked together and then cut. Okay, so these are what we'll see as uh, form then bond and bond then form techniques. Now, what are the different mechanisms that are used to achieve bonding between these different layers? First is gluing or adhesive bonding, which we'll commonly understand like we apply Fevicol or any kind of glue to bond multiple sheets of paper together. Then we have thermal bonding processes wherein heat will be employed. Thermal name suggests heat will be employed to effectively bond multiple stacks or multiple sheets together. Third one is the clamping, which is more of a mechanical aspect wherein you'll be using nuts and bolts to clamp multiple sheets together. And then last is ultrasonic welding or ultrasonic consolidation. This is ultrasonic consolidation. Okay. So let us see each one of these in details. As I had mentioned earlier, this gluing or adhesive bondings, it occurs in two mechanisms. First is bond, then form process. And other one is form, then bond process. Here, first stacking and then cutting. And here cutting and then stacking. Okay. So now for for bond then form process, what will be the sequence? You'll place the laminates and bond it to the substrate using heated rollers. Okay, so these heated rollers will just move over or roll over your laminate, and because of the heat, the adhesive that is present on the back side of the laminate, adhesive adhesive is present on the back side of the laminate. And now when this laminate is processed through the heated rollers, okay, after passing through the heated rollers, okay, this adhesive melts and bonds. And bonds the laminate. Now once this bonding is done, then this laminate is cut according to the slice contour or according to the geometry that you have prescribed. Now the second method is form then bond, cutting and then stacking. So suitable sheet material with an adhesive backing is placed on a carrier and then it is cut to the outline of the desired cross section. So your suitable sheet material, it is placed on a carrier which will carry the sheet, and it is cut based on the cross sections or the CAD geometry. Now this shaped laminate is positioned on top of the previously deposited layers. So you will be at other place you will be having a stack wherein you are continuously placing your shaped laminate. Then you will take your cutted laminate from the carrier towards that stack of yours and then bond it together using that adhesive that is present on the back side. And this process is continued till the part is completed. Now, next is thermal bonding. So this thermal bonding usually uses the conventional form then bond process. Okay, it majorly uses this form and then bond process, and for manufacturing metal parts. So it is majorly used for metal part fabrication. So here we see that this thermal bonding has been applied successfully to these metallic parts, and that too without any sharp gradients or discontinuities at the interface. So you have these two laminates. Okay, 1, 2. So here this is more of a continuous regime. So this interface is continuous, and any discontinuities that are because of may arise because of two different lamellates are absent. Okay, so there are continuous grain structures along this interface. For example, Al4343 coating material, they are bonded together by heating the assembly in a nitrogen atmosphere just above the melting point. Okay. Okay. Now, third process is the processes based on sheet metal clamping. So this is basically used for rigid metal laminates where it is difficult to pass them through the rollers and they will not respond to the forces that can be applied there. So we use these clamping mechanisms wherein the sheets can be held together and clamped using bolts or other clamping mechanism. For example, you just put a kind of stapler pin on a stack of paper. So that is your clamping. So similarly for metals, there are nuts and bolts and other clamping mechanisms. So the major advantage is that you can quickly disassemble these for any kind of changes in the geometry or modifications. Quick disassembly for easy modification of the parts and repairing, quick modification of the parts and then repairing of your objects in case there are any wear and tear. Now the last one was ultrasonic condensation consolidation. Okay, so it is a kind of hybrid sheet lamination process. So it is a hybrid sheet lamination process, okay, that combines ultrasonic metal seam welding and CNC milling. So it is a combination of ultrasonic seam welding and CNC milling. Okay, so in ultrasonic condensation, the object is built up on a rigidly held base plate, which is bolted on a heated plate. So here you can see this is the heated base, and this is your object. Okay, so this is these are two parts: heated base, and sorry, this is the base plate, and below this is your heater, so which helps in heating, and over this is your part built. Now parts are then built from bottom to top. You can see building direction is this. So this is your building direction. Okay, this is your building direction. Okay, from bottom to top, and each layer is composed of several metal foils. So we had already discussed that in laminated object manufacturing, you have different 2D sheets stacked over one another. So it is composed of several metal foils, and then it is trimmed using CNC milling. Okay, so these foils are then trimmed using CNC milling so that you get the final contours of your object. Okay, so this was ultrasonic seam welding and CNC milling. So, and during this process, you have a sonotrod. It keeps on rotating along the path at a particular speed. And why it keeps on rotating? So as the foils, they are held in contact with the base plate or the previous layer, and they are bonded together in a proper manner. Okay, so this sonotron, this applies sufficient pressure or force to help the metallic foils to remain in close contact with the base plate or the previously bonded layer, so that you have a coherent solid structure. If this bonding is not good enough, then your structure will just collapse or fail under certain shear forces or tensile forces. And then what are the important controllable process parameters for this ultrasonic consolidation? These are oscillation amplitude, normal force, travel speed, and the temperature. So how is oscillation amplitude important? So oscillation amplitude defines the input energy, defines the energy input. Okay, so whatever there are oscillation, it directly affects the elastic and plastic deformation between the mating metal interfaces. Okay, and for a given material combination, oscillation amplitude and frequency of the sonotron determines the amount of ultrasonic energy available. So this your oscillation amplitude plus frequency, this gives your energy, ultrasonic energy available. Okay, and so that you can now adjust this amplitude and frequency as per the energies that are required for proper bonding. Now this normal force is the force applied by the sonotron when pressing the different layers. Okay, so this sonotron is rolling over this multiple layers and it is applying force. So a particular threshold force is required which helps in proper consolidation of the different layers. Okay, so that force criteria should be met, so has to have proper consolidation. Now you have sonotron traveling speed. Okay, so the in this ultrasonic consolidation welding, this exposure time is directly determined by the travel speed. Higher the exposure time, smaller will be the speed. Okay, slow speed is equals to higher exposure times, and better will be the bonding. Okay, so but at too high speeds you can also cause damage. Too high speed, sorry, too high exposure times can cause damage. So you need to optimize. That is not, it should not be too slow so as to damage the part, and it should not be too fast so as not to join them effectively. And the last one is the temperature. So these metallurgical bonds, they can be established at a particular temperature only. Metallurgical bonds are established at particular temperatures. So you should try and always maintain those temperatures so that, and provide preheat so there is proper consolidation. Okay. So this was all about this laminated object manufacturing. Now, in case you have any questions, you guys can ask them. Else we'll now start moving towards the sample problems for this week. So any questions from anyone? Okay, so we'll start with the sample problems now. Okay, the first question is, if the pressure remains constant, the resulting extruded material will flow at a constant rate and will have a constant cross-sectional diameter. True or false? So if the pressure is remaining constant pressure, and you have a fixed cross-sectional area to pass through the nozzle. Okay, so constant pressure means you have constant flow rate. Okay, and when your flow rate is constant, you will have a flow rate is constant, that means a fixed velocity or a fixed mass per unit time, sorry, not velocity, fixed mass flow per unit time, and this will ensure a constant diameter as well. So the correct answer is true. So for the next question, question 2, which of the following features are common to any extrusion based system? Loading of the material, liquefaction of the material, application of pressure to move the material through the nozzle, or all of these. So we saw a complete list of 7 features. So I'll just quickly make a schematic of what was done. So these were your heating chambers, and then you had this filament or your material. So this is your filament, and then you had your pinch feed rollers. These are your pinch feed roller systems. Okay, so this filament comes under loading of the material. And this heating chamber, this helps in liquefaction from solid to a semi-solid or molten state. And these pinch feed rollers, they rotate in this direction and allow the movement of filament towards this liquefaction chamber. So they apply pressure. So their function is to apply pressure to move the material through the nozzle. Okay, so all these options, given options, are features of a common extrusion based system. Now moving on to question 3. Okay, in case you have any doubts in any of the questions, you can just stop me in middle. So we'll move to question 3. The extrusion method works on the principle that what is held in the chamber will become liquid that can eventually be pushed through the die or the nozzle. So moving to the schematic that I draw for question 2. So here this is an extrusion based system, and it indeed using a heating chamber that allows for the liquefaction of the material. And once that material is in the semi-solid or kind of a molten state, then only can it be extruded. Imagine if the toothpaste was a complete solid. Would it have been possible for you to just take it out of the tube by applying certain pressure? Obviously not. So on similar principles or similar lines, this extrusion based methods have been developed, wherein the material that is held in the chamber will become liquid that can eventually be pushed through the die or the nozzle. So the answer is true. Question 4. The extrusion nozzle does not determine the shape and size of the extruded filament. True or false? Okay, so now imagine if you are having a kind of nozzle which is having a circular cross section. So this is your nozzle which is having a kind of circular cross section. So whatever material is extruded through it will obviously take the shape of this circular cross section. So the cross section will be circular. Had this nozzle been having a square cross section, so whatever material would have been extruded, it would have been in the form of a cube or a square cross section. And how can the diameter of the extruded material or size of the extruded filament be larger or smaller than the diameter of the nozzle? That is not possible. So the answer is false. The nozzle does determine, the extrusion nozzle determines the shape and size of the extruded filament. Okay. Now moving on to question 5. The diameter of the nozzle determines the minimum feature size that can be created. True or false? The answer is true. Suppose your nozzle diameter is 0.5 mm. And you want to make a cylinder. Okay, now your objective is to make a cylinder of dia 0.1 mm. So whatever this nozzle is extruding, it is already of 0.5 mm. So you cannot just remove these materials. The material cannot be removed until it is in hybrid machine. So now this what minimum dia can it print? It is 0.5 mm. So this is the least feature size that can be printed using this machine. So the answer is true, and it is determined by the diameter of the nozzle. Now question number 6. Extrusion based processes are more suitable for smaller parts. Okay. So what shall be the correct answer? Extrusion based processes are more suitable for smaller parts. Can anyone answer for this? Okay. Anyone up for this answer? Okay, just allow me a minute. Okay, so the answer for this is true. Let me confirm the answer once first. Okay, sorry. The answer for this part is false. Extrusion based processes are more suitable for larger part fabrication. So the correct answer is false. Okay. Question number 7. Once the material is extruded, it should ideally retain the same shape and size. True or false? Of course, it should retain its shape and size. If it doesn't retain shape and size, then what is the entire point of developing any material? So, the material should always maintain its structural integrity. Okay? So, it should not lose its shape and size. Question 8. If the material is extruded in the form of a gel, the material generally dash upon drying. Shrinks, expands, both of these, none of these. So the material usually shrinks. Why it shrinks? So it is in the form of a gel. That means it is having some water or solvent content. And when this part will dry, these two, these will evaporate. Okay, and this evaporation will in turn cause shrinkage. Okay, so answer is they shrink upon drying. Question number 9. All rapid manufacturing systems must have a means for supporting freestanding and disconnected features and for keeping all features of a part in place during the fabrication process. True or false? So let us understand what is freestanding. Freestanding are your basically overhang parts. Freestanding are and disconnected features these refer to any kind of overhang or complex geometries. Okay, so obviously all many rapid manufacturing systems should handle these very carefully, and there should be features present in them so that they can cater to the requirements of such geometries. So the answer should be true. The last question for today is, if the non-linear effect is significant for cooling, it is possible that the resulting part will distort upon cooling. So what is this non-linear effect? So it is the difference in the cooling rates for different parts of the geometry, different sections of the build part. So if your part is something like this, suppose, so here it is thin, here it is thick. So in both the section, your cooling rates will be different. So in such a scenario, when cooling rates are different, these parts can easily undergo distortion because there is kind of a thermal mismatch between them. So one will cool at a faster rate and one at a slower rate. So one will be having faster changes in dimensions and the other will be having slower changes, so which are not compatible with each other and will ultimately cause distortion. So the correct answer is true. So these were the questions for today and the brief recap of the week's content. In case any one of you have any questions, you can ask them now. So all these presentations and lecture videos will be available to you through YouTube links and Google Drive links. And you can ask your questions now in the interaction sessions, or you can post them on the discussion forums. Okay, so I think we can wrap the session for today. Thank you everyone for joining in. Let's meet in the next session on next Saturday at 5 p.m. Thank you everyone.